The universe began in a state of almost perfect simplicity. For billions of years, it contained nothing but the most basic particles, a cosmic sea of hydrogen and helium. Yet somehow, from that barren emptiness, the first intricate chemical structures emerged. These were the universe's first complex molecules, the silent architects of everything that followed, including us. This is the story of their impossible birth. By the end, you will have explored 30 distinct scientific theories that attempt to crack this fundamental cosmic mystery. Did these building blocks of life cook in the oceans of newborn planets, or were they forged in the cold depths of space between the stars? What do you believe sparked the journey from chemistry to biology? The journey from simple atoms to complex chemistry had to begin somewhere, and for decades, one idea has stood as the iconic starting point. It is called the primordial soup theory, a concept so deeply woven into our understanding of life's origins that its name feels almost mythical. Picture a young, violent Earth, its surface a churning global ocean under a sky choked with volcanic gases. Within this chaotic nursery, the theory proposes the first organic molecules were cooked into existence. Energy from lightning strikes, intense ultraviolet light from the young sun, and the planet's own geothermal heat acted like a cosmic chef, stirring a broth of simple chemicals into something far more interesting. This is not just a poetic idea, it was tested in a landmark experiment in the 1950s. Two scientists, Stanley Miller and Harold Urey, built a glass apparatus to mimic these ancient conditions. They filled it with water, methane, ammonia, and hydrogen, gases thought to compose the early atmosphere, then passed electrical sparks through the mixture to simulate lightning. Within days, the clear water turned a murky pink and brown. When they analyzed it, they found amino acids, the fundamental building blocks of proteins and, by extension, life itself. It was a staggering result, one that seemed to solve the mystery in a single, elegant demonstration. Life, it suggested, was an inevitable chemical process on a suitable, wet, rocky world. But what if the kitchen was not a planet, but the cosmos itself? The principles of the Miller-Urey experiment scale up. Imagine not a flask on a lab bench, but the vast, warm puddles on the surface of a young Mars, or the subsurface oceans churning beneath the icy crust of moons like Europa or Enceladus. Consider the mineral-rich pools that might have formed on asteroids still warm from their own formation. In these environments, the same cosmic recipes could have been at work. Ultraviolet radiation from nearby stars, cosmic rays, and the immense electrical discharges of planetary lightning could have provided the spark. Instead of a single planetary soup, the galaxy may have been simmering with countless such cauldrons, each a potential birthplace for complexity. This theory paints a picture of a universe that is inherently fertile, where the ingredients for life are not rare exceptions, but a common outcome of planetary geology and chemistry. It grounds the mystery in a place we can almost touch, on the familiar, rocky surfaces of worlds. Yet for all its power, this theory immediately raises a profound new question. If these complex molecules formed so readily on warm, wet planets, how did they survive the journey to become something more? The early solar system was a shooting gallery of colossal impacts, one of which likely gave us our moon. Any delicate organic broth on the surface would have been vaporized, sterilized, erased. So, did life's ingredients need a safer, quieter place to assemble? Perhaps the building blocks did not need to survive the planetary chaos because they never originated there. This leads us to a theory that turns the entire mystery inside out: panspermia. The idea is audacious in its simplicity. The first complex molecules, and perhaps even the very seeds of life, did not form on Earth at all. Instead, they were cosmic hitchhikers delivered to our young planet by celestial messengers like comets, asteroids, or even interstellar dust grains. In this view, Earth was not a kitchen but a dining table set with ingredients shipped in from across the galaxy. The evidence for this is not just speculative. We have caught these cosmic couriers red-handed. Space probes have analyzed the comas of comets and found them rich in organic material, including the amino acid glycine, one of the fundamental compounds that make up proteins. Meteorites that have crashed to Earth, carbonaceous chondrites, are studded with a menagerie of complex organic molecules, from sugars to nucleobases, the very letters of our genetic code. These are not contaminants from our world. They are ancient, pristine samples of the chemistry occurring in the cold dark between the stars. The most compelling question then becomes one of survival. How could such delicate structures endure a violent impact or the brutal radiation of deep space? Remarkably, experiments show that some organic compounds are far hardier than we once imagined. Within the protective rocky or icy matrix of an asteroid or comet, molecules can be shielded from the most damaging cosmic rays. The outer layers might get scorched, but the precious cargo deep inside remains frozen in time, preserved for millions or even billions of years. Furthermore, the vacuum of space itself, while extreme, lacks the reactive oxygen and liquid water that can break down complex chemistry on a planet. In a strange way, the cold, empty void can act as a perfect preservative. This theory dramatically expands the stage for life's origins. It suggests that the process of creating life's ingredients could have begun in the solar nebula before Earth even formed, or in the molecular clouds that birthed our sun. A single, fortunate impact on one world could then scatter its biological potential across an entire planetary system. So we are left with two profoundly different origin stories. Was our planet a prolific, self-contained chemical factory, or a fertile garden sown with seeds from the stars? The answer may not be one or the other, but a combination of both, a cosmic collaboration that set the stage for everything to come. The deep ocean offers a radically different kind of cradle, one shielded from the celestial violence above. Far beneath the waves on the dark ocean floor of a young Earth, otherworldly chimneys rise from the crust. These are hydrothermal vents, and they present a compelling case for where life's chemistry truly began. Forget the sunlit surface soup. This theory suggests the first complex molecules were forged in perpetual darkness under immense pressure at the razor's edge between boiling and freezing. The chemistry here is unlike anything on the surface. Superheated water, often reaching temperatures over 700 degrees Fahrenheit, erupts from the seafloor, saturated with minerals and gases like hydrogen sulfide leached from the surrounding rock. This scalding, chemical-rich fluid immediately meets the near-freezing seawater of the deep ocean. The collision is not chaotic, it is generative. It creates stable gradients of temperature, acidity, and chemical concentration that persist for millennia. Within these gradients, energy is not a fleeting lightning bolt. It is a constant, reliable force. Crucially, the vents themselves are not just sources of heat. They are intricate structures built from porous minerals, particularly iron-sulfur compounds like pyrite, often called fool's gold. These mineral surfaces are thought to have acted as the universe's first catalysts and templates. Imagine a microscopic honeycomb of iron and sulfur, its repeating geometric structure providing a perfect, stable landing pad for simple molecules like carbon monoxide and hydrogen. On these warm, catalytic surfaces, the molecules could link together step by step, building chains into more complex organic compounds, protected within the tiny pores of the rock from being torn apart again by the surrounding water. This process, called chemosynthesis, uses chemical energy rather than sunlight to power construction. It turns the entire concept of a hospitable environment on its head. Life's precursors may not have needed a calm, warm pond, but a dynamic, mineral-rich, chemical-powered reactor. The vents provide everything in one package: a continuous energy source, a rich supply of raw materials, and a safe, structured environment for molecules to experiment with complexity. This theory elegantly solves a major puzzle of surface-based origins: how to protect delicate early chemistry from the sterilizing ultraviolet light of the young sun. In the abyssal dark, that problem simply never existed. So we now have three powerful possibilities: a sunlit planetary soup, a delivery of cosmic ingredients, or a deep-sea chemical forge. But what if the answer is not a location, but a process, a fundamental law of chemistry that operates everywhere? The violent energy of a young planet or the gentle chemistry of a deep-sea vent are not the only forces capable of building complexity. There is another, far more relentless power source that permeates every corner of the galaxy: cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, hurled across space at nearly the speed of time itself by supernova explosions and other cataclysmic events. They are a constant, invisible rain of high-energy particles, and they may have been the universe's first chemists. This theory proposes that the cold, dark molecular clouds where stars are born are not dormant chemical graveyards, but active laboratories powered by this ceaseless bombardment. Within these vast, frigid clouds of gas and dust, temperatures hover just a few degrees above absolute zero. Under normal circumstances, chemistry here should be frozen in place, atoms and simple molecules locked in a state of near-permanent stillness. The energy required to make them react and form new bonds simply does not exist in the ambient heat. But cosmic rays change everything. When one of these ultra-fast particles smashes into a simple molecule, like a clump of hydrogen and carbon monoxide frozen onto a speck of dust, it delivers a tremendous, localized shock of energy. This violent encounter can shatter the molecule into reactive fragments, charged atoms and molecular pieces known as radicals, which are desperate to form new connections. In the aftermath of the collision, amidst the chaos, these hot, excited fragments find each other. They have the activation energy, the necessary spark, to overcome the barrier that normally keeps them apart in the cold. They begin to link together, forming new, more elaborate structures right there on the surface of the dust grain. It is a bit like using a hammer to build a watch. The initial impact is destructive, but from the scattered pieces, new and more intricate assemblies can emerge. This process can build molecules of surprising complexity, from simple alcohols like methanol to more elaborate chains. The dust grains themselves act as a crucial third player, their surfaces providing a stable platform where these newly formed radicals can meet and combine before they drift apart or are destroyed. Over millions of years, this slow, steady process of cosmic ray bombardment could enrich entire interstellar clouds with a rich organic haze, a pre-made inventory of life's potential ingredients before any planets have even formed. This theory elegantly bridges two worlds. It explains how complex chemistry can arise in the deepest cold of space, far from the warmth of stars or planets, creating a universal feedstock that could then be delivered to new worlds via comets and asteroids. So the question shifts: is the universe not just a place where chemistry happens, but a place where it is constantly being jump-started by its own most violent phenomena? But where exactly do these cosmic ray-driven reactions take place? They need a stage, a solid surface where the scattered pieces can linger long enough to find each other. That stage is smaller than you can possibly imagine, yet it is everywhere. It is interstellar dust. These are not the fluffy particles in your home, but microscopic motes of silicate rock or carbon, smaller than a wavelength of light, born in the atmospheres of dying stars and scattered across the galaxy. In the vast emptiness between stars, these tiny grains become the universe's most fundamental chemical workshops. Picture a single dust grain floating in the profound, cold, and near-perfect vacuum of a molecular cloud. It is an island in a sea of nothingness, and its surface possesses a strange and powerful property. Atoms and simple molecules drifting through the cloud, like hydrogen, carbon monoxide, and water vapor, do not simply bounce off. In that extreme cold, they lose their thermal energy. When they touch the grain's surface, they stick, frozen in place by feeble intermolecular forces in a process called adsorption. Over thousands, then millions of years, a thin frost of these simple compounds builds up layer by layer. This icy mantle is not inert, it is a chemical waiting room. The dust grain shields the frost from the most damaging ultraviolet radiation, creating a relatively safe environment, but it is still bathed in that steady, invisible rain of cosmic rays. When a high-energy particle strikes, it does not just energize the molecules, it can also knock atoms loose from the grain's own structure, adding new raw materials like silicon or metals to the mix. Now trapped together on this microscopic platform, the frozen molecules are in constant, slow-motion intimacy. They are close enough to react. The energy from cosmic rays or even from the faint warmth of a distant star provides just enough of a nudge. A hydrogen atom, liberated by a cosmic ray hit, might skitter across the icy surface until it meets and bonds with a carbon monoxide molecule, beginning a chain of reactions. Through this slow, patient process known as surface chemistry, simple two-atom molecules can grow into long carbon chains, alcohols, and even the ring-shaped structures of prebiotic compounds. The dust grain is more than a passive platform. Its crystalline structure can act as a template, guiding how molecules align and connect, favoring the formation of specific, more complex shapes. Over astronomical timescales, these grains become coated in thick, organic-rich mantles, essentially tiny frozen chemical libraries. When a shock wave from a nearby supernova or the gentle pressure of a forming star compresses the cloud, these grains, with their precious cargo, are incorporated into new comets and asteroids. They become the delivery vehicles for pre-made complexity. So the humble interstellar dust grain, invisible to the naked eye, may have been the essential crucible where the universe's first complex chemistry quietly assembled itself, one frozen reaction at a time, long before the first star or planet ever called it home. This reveals a universe where complexity is not a rare accident, but a baked-in process, a slow cosmic craftsmanship occurring on a trillion tiny anvils. The cold, dark molecular cloud was not the end of the story for those dust grains. Gravity began to pull, the cloud collapsed, and at its center, a new star ignited. Around that infant sun, the remaining material did not simply vanish. It flattened into a vast, spinning disk of gas and dust, a protoplanetary disk. This was the nursery for planets, and within its dynamic chaos, a new chapter of chemical complexity was about to be written. Here, the primary energy source shifted from the random violence of cosmic rays to a more constant, directional force, the intense ultraviolet light blazing from the young star itself. This theory suggests the swirling disk was not just a construction site for worlds, but a sprawling photochemical reactor. Imagine those same dust grains, now coated in their thin frost of simple ices, swept into this warmer, more energetic environment. They are no longer drifting in a uniform dark cloud, but orbiting in a disk with dramatic gradients, hot and brightly lit near the star, cold and shadowy in the outer reaches. The star's fierce ultraviolet photons act like tiny, precise tools. When one strikes a water-ice molecule on a grain's surface, it does not just warm it, it can break it apart, creating highly reactive fragments like hydroxyl radicals. These fragments are desperate to bond with anything nearby. A carbon monoxide molecule frozen right next door becomes the perfect target. Step by step, through a cascade of these light-driven reactions, the simple ices are rebuilt into more complex organic molecules, things like formaldehyde, methanol, and even the precursors to amino acids. This process has a powerful advantage over random cosmic ray collisions. Ultraviolet light is abundant and its effects are more predictable, allowing for specific, repeatable chemical pathways to emerge. The location within the disk is everything, too close to the star, and the heat is so intense it would vaporize the ices and shatter any complex molecules. Too far out, and the ultraviolet light is too weak to power the reactions. But there is a sweet spot, a region often called the molecular formation zone, where conditions are just right, cold enough for ices to survive, but bright enough for photochemistry to thrive. In our own solar system's history, this zone likely existed in the space now occupied by the asteroid belt and the outer planets. Here, for millions of years, trillions of dust grains became microscopic factories, their surfaces constantly processing simple ices into a richer organic inventory under the young sun's glare. Then, as planets began to coalesce, these processed grains were swept up. They became the building blocks of asteroids and the icy cores of comets, locking that photochemical heritage into the very bones of the solar system. This theory provides a direct link. It explains how the generic organic haze of interstellar clouds could have been upgraded and customized right here in our own cosmic neighborhood, creating a unique chemical starter kit for the planets that would follow, including Earth. The disk was not a passive conveyor belt of raw materials. It was an active processing plant, imprinting its own chemical signature on everything it would later create. But the most spectacular chemical forges in the universe were not gentle or gradual. They were born from its most violent deaths. When a massive star exhausts its fuel, it does not fade quietly. It collapses, then explodes with the brightness of an entire galaxy, a supernova. In its final, catastrophic act, the star blasts its own enriched guts across light years of space, creating a seething, expanding shell of debris and energy called a supernova remnant. And within that chaos, a radical theory suggests the shock waves themselves may have forged the universe's first complex molecules. This is shock wave synthesis, chemistry at the edge of apocalypse. Picture the aftermath, a titanic wall of superheated plasma moving at millions of miles per hour, slams into a quiet, cold molecular cloud that has been drifting nearby for eons. The collision is unimaginably violent. The shock wave does not just push the cloud, it compresses it, crushing the gas and dust to densities thousands of times greater than before. In an instant, the serene cold is replaced by searing heat, as friction and compression raise temperatures to thousands of degrees. But this is not a simple incineration. It is a sudden, extreme pressure cooker. Within that fleeting moment of intense heat and density, the normal, slow rules of interstellar chemistry are shattered. Simple atoms and molecules like carbon, oxygen, and hydrogen are forced into a frenzied dance of collisions. They have so much kinetic energy that they overcome the normal barriers to reaction, slamming together to form new, more robust bonds at a breakneck pace. The shock wave provides both the raw force and the perfect, transient conditions. As the compressed gas rapidly expands and cools behind the shock front, the newly formed molecules are suddenly frozen into existence, locked into their complex forms before they can be torn apart again by the ongoing violence. What kinds of molecules could survive such an inferno? Laboratory experiments and sophisticated computer models suggest the list is surprisingly long. Under these extreme conditions, the formation of hardy ring-shaped molecules like polycyclic aromatic hydrocarbons, essentially the sooty building blocks of more complex organics, becomes not just possible but probable. Even precursors to amino acids and the nucleobases of RNA could be synthesized in this furious, all-at-once event. Think of it not as a gentle simmer, but as a flash of cosmic lightning, etching complex chemistry onto the canvas of space in an instant. The profound implication is that these stellar explosions did not just create the heavy elements necessary for planets and life. They may have also jump-started the very chemistry of complexity itself. A single supernova could have enriched not just one, but many nearby star-forming clouds with a fresh, rich infusion of prebiotic material. The death of one star becomes the chemical awakening for the next generation. This paints a universe where creation and destruction are two sides of the same coin, where the seeds of future life are sown in the fire of a stellar grave. So we must ask, if such cataclysms were the original chemists, is the chemistry of life itself an echo of ancient explosions written into the fabric of our very atoms? Yet another source of energy was quietly at work, one that required no violent collisions or brilliant starlight. It was the silent, persistent warmth of atoms falling apart. In the very rocks that built the solar system, radioactive elements were ticking away like tiny geological clocks, and their decay provided a perfect, gentle heat for chemistry. This theory centers on an isotope called aluminum-26. Unlike the stable aluminum we know today, this version was unstable, radioactive. It was forged in the same supernova explosions that seeded our neighborhood with heavy elements, and it was incorporated into the first solid bodies to form around the young sun, the asteroids and planetesimals. Aluminum-26 has a half-life of about 700,000 years, a geological blink of an eye. As it decayed, it released a steady stream of heat from within the heart of these rocky bodies. For millions of years, this internal warmth was transformative. Imagine a medium-sized asteroid a few dozen miles across, composed of rock, metal, and rich veins of water ice. Initially, it is a frozen, lifeless lump in the dark, but as the aluminum-26 atoms within its rock decay, they release energy. The interior begins to warm, not to scorching temperatures, but to a range just above freezing, perhaps between 32 and 100 degrees Fahrenheit. This is the sweet spot for liquid water. The ice deep within the asteroid melts, creating subsurface pockets and networks of briny liquid. Now the stage is set. Within this dark, watery environment, shielded from the harsh radiation and impacts of the early solar system, the dissolved minerals and simple organic compounds already present in the ice and rock begin to interact. The gentle, pervasive heat from the radioactivity acts as a constant driver for chemical reactions. It provides the activation energy needed for molecules to link into longer chains without the destructive violence of a lightning strike or a cosmic ray. This warm, wet, rocky interior becomes a natural, long-duration chemical reactor. Over thousands of years, this process could have produced a diverse suite of complex organic molecules. The surrounding mineral matrix, much like the surfaces of deep-sea vents, could have catalyzed specific reactions, guiding the chemistry toward greater complexity. The beauty of this theory is in its longevity and protection. While surface environments on planets were being sterilized by impacts, these subsurface asteroid laboratories were safely insulated, cooking their organic chemistry for eons. Eventually, many of these asteroids would be shattered by collisions, scattering their chemically processed, water-rich fragments across the solar system. Some of those fragments, as meteorites, would later fall to Earth, delivering not just water, but a pre-made inventory of complex organics that had been slowly, patiently assembled in the dark, powered by nothing more than the silent heartbeat of decaying atoms. It suggests that the building blocks of life might have been an inevitable byproduct of planetary construction, baked into the very process of making rocky worlds. While supernovas forged elements and asteroids simmered with radioactive warmth, a quieter chemical thread was weaving itself through the cosmos. Its name is formamide, and it may have been the master key that unlocked life's molecular diversity. Detected in the cold clouds of interstellar space and even in the comas of comets, formamide is a deceptively simple molecule, just one atom each of carbon, oxygen, and nitrogen, with a few hydrogens attached. Yet under the right conditions, this humble compound possesses a remarkable chemical versatility. It can transform, almost like a universal adapter, into the very letters of the genetic code and the links of protein chains. The formamide pathway theory suggests this one molecule was a central hub in prebiotic chemistry, a crossroads where many roads to complexity converged. How does this transformation work? Imagine formamide as a chemical Swiss Army knife. when it is exposed to an energy source like the ultraviolet light bathing a protoplanetary disk or the gentle warmth of a radioactive asteroid interior, its structure becomes activated. The bonds between its atoms loosen, making it highly reactive. In the presence of common minerals or even simple catalysts like clay, this activated formamide can undergo a series of elegant rearrangements and additions. A phosphorus-bearing mineral might donate a phosphate group. A stray molecule of hydrogen cyanide, also common in space, might add a nitrogen ring. Through these steps, formamide can be coaxed into becoming nucleobases, the information-carrying molecules like adenine and guanine that form the core of RNA and DNA. In a slightly different reaction pathway, perhaps with a splash of water and a different mineral catalyst, those same formamide molecules can stitch themselves into amino acids, the building blocks of proteins. This is not a speculative fantasy. Laboratory experiments have successfully demonstrated these transformations under conditions that mimic the early solar system. A single starting material, subjected to the generic energies available in space or on a young world, branches out to create two of the most critical families of biomolecules. The power of this theory is its elegant parsimony. It proposes that the universe did not need to invent dozens of separate, improbable chemical routes to create life's toolkit. Instead, nature may have found one efficient, robust pathway that, under a variety of common cosmic conditions, could reliably generate a whole suite of essential ingredients. Formamide becomes a chemical seed crystal, dropped into the primordial environment from which an entire garden of complexity could grow. This shifts our perspective from searching for where specific molecules formed to understanding how a universal chemical intermediate could have been processed by the environment. It paints a picture of a cosmos not just stocked with random organic parts, but one that follows a built-in chemical logic, a set of instructions written not in code, but in the inherent reactivity of matter itself. If formamide was such a potent precursor, waiting in the ice of comets and the dust of nebulae, what force was needed to finally read those instructions and begin the assembly? The universe's chemical logic needed a solid surface to write upon. Among the most abundant and unassuming materials on any young, wet, rocky world is clay. This simple dirt may have been the universe's first notepad, a physical template that gave chaotic chemistry a sense of direction. The theory of clay mineral catalysis suggests these humble minerals did far more than just get muddy. They actively guided the assembly of life's first complex molecules. Clays like montmorillonite are not just fine-grained dirt, they possess a remarkable microscopic architecture. Picture them as stacks of incredibly thin, negatively charged sheets like pages in a book. Between these sheets are layers of water and positively charged ions, creating a dynamic, organized landscape at the molecular scale. When simple organic compounds, like the activated nucleotides that could form RNA, washed through a puddle or stream on the early Earth, they were not ignored. The charged surfaces of the clay acted like a magnet, attracting and concentrating these scattered molecules directly onto their sheets. This was the first crucial step, gathering the raw materials from a dilute solution into one productive place. But the clay did more than just collect, it also organized. The geometric patterns of atoms on the clay's surface provided a perfect template. Imagine trying to string beads onto a necklace in a storm, nearly impossible if they are flying everywhere. But if the beads are first laid out in a neat row, held in place by tiny grooves, the task becomes simple. The clay's surface likely did exactly that, holding the simple molecular building blocks in just the right orientation and alignment, side by side, so that their reactive ends were poised to connect. Then, using the energy from something as ordinary as the sun's warmth or the gentle heat of a geothermal spring, the clay could catalyze the final act, polymerization. The molecules linked together, forming chains right there on the mineral surface. Experiments have stunningly demonstrated this, showing that clays can facilitate the formation of RNA strands over 10 units long from simple precursors. a huge leap toward a molecule capable of storing information. This process would have been incredibly robust on the early Earth or even on a wet, early Mars. Clay minerals form readily when water interacts with volcanic rock, meaning they would have been ubiquitous along shorelines, in river deltas, and in muddy pools. These environments provide the perfect cycle: wet periods to dissolve and mix chemicals, and dry periods to concentrate them on the clay surfaces where the linking reactions are favored. The clay itself is not consumed. It is a reusable platform, a persistent stage upon which the play of complexity could be rehearsed over and over. This theory grounds the mystery in something profoundly tangible. It suggests that the path from simple chemistry to complex, information-carrying polymers may have been a natural geological process, as inevitable on a wet, rocky planet as erosion itself. The first complex molecules may not have been floating free in a soup, but literally embedded in the mud, their very structure imprinted by the crystalline order of the Earth beneath them. If dirt could guide the formation of genetic material, what other common mineral might have held a different piece of the puzzle? Extreme cold is not the absence of chemistry, but a different kind of laboratory. Within the dense, dark hearts of molecular clouds, temperatures plummet to just a handful of degrees above absolute zero. Here, the frenetic dance of atoms we associate with chemical reactions seems impossible. Motion is nearly frozen, and the energy needed to break and form bonds appears utterly absent. Yet, paradoxically, this profound cold is precisely what allows a unique and delicate form of chemistry to unfold. In the warmth of a planet or the heat of a star, molecules collide with such violence and speed that complex, fragile assemblies are often shattered before they can stabilize. The cold changes the rules entirely. In this near stillness, molecules and atoms drift with glacial slowness. When they encounter one of the ubiquitous dust grains, they do not bounce away. Instead, they lose their minuscule thermal energy and simply stick, frozen in place by weak intermolecular forces. This process, called adsorption, creates a thin, icy mantle on each grain, a frost of simple molecules like hydrogen, carbon monoxide, and water. Now trapped together in this frozen matrix, the reactants are held in intimate, prolonged contact. They have all the time in the universe. The reaction itself proceeds not through forceful, energetic collisions, but through two subtle quantum mechanical processes that only work efficiently in the cold. The first is surface diffusion. Even in that deep freeze, atoms and molecules are not completely motionless. They possess a tiny amount of quantum mechanical zero-point energy, allowing them to shuffle and vibrate in place. Occasionally, this allows a hydrogen atom, for example, to hop from one frozen site to an adjacent one on the dust grain surface, like a slow-motion game of molecular checkers. The second, even more fascinating process is quantum tunneling. In the warm world of classical chemistry, two molecules need to physically smash together with enough energy to overcome a repulsive barrier, like rolling a ball over a hill. In the quantum realm of the molecular cloud, that hill still exists, but incredibly small particles like hydrogen atoms do not always need to go over it. There is a probability they can simply appear on the other side, as if passing through a tunnel in the hill itself. This tunneling probability is vanishingly small for large molecules, but for the lightest atoms, it becomes a significant pathway, especially when everything else is moving so slowly. So, a hydrogen atom frozen next to a carbon monoxide molecule on a grain of dust can slowly, over months or years, tunnel through the energy barrier and form a new chemical bond, creating formaldehyde. This new molecule might then be visited by another tunneling hydrogen, building complexity one painstaking step at a time. This slow, cold chemistry is incredibly selective and gentle. It favors the formation of specific hydrogen-rich molecules and can build surprisingly complex organic species like methanol and even the precursors to sugars without ever raising the temperature a single degree. The entire molecular cloud becomes a vast, three-dimensional factory operating in ultra-slow motion. Its countless dust grains each serving as a cryogenic workbench where the universe's first complex molecules are assembled with infinite patience. This reveals a cosmos where life's ingredients are not forged solely in fire, but also in the silent, deliberate cold, through rules that defy our everyday intuition. If such delicate constructions can form in the void, what protected them when their quiet nursery was shattered by the birth of a star? The quiet chemistry of cold molecular clouds was a universe away from the hellscape of a young volcanic planet. Yet that very violence may have been the crucible for another pathway to complexity. Early Earth and likely Mars and Venus were worlds of fire, their surfaces scarred by countless eruptions. But the real chemical magic happened not in the lava, but in the sky above it. When a volcano erupts, it does more than spew molten rock. It launches a colossal plume of superheated gases, ash, and water vapor miles into the atmosphere. This churning, turbulent column becomes a colossal natural battery. The countless ash particles colliding within the plume generate tremendous static electricity, sparking continuous, violent lightning discharges that flicker through the ash cloud. This creates a planetary-scale version of the Miller-Urey experiment, a natural reactor operating with raw geologic power. The volcanic gases themselves provide the perfect feedstock. Instead of a sterile mixture of carbon dioxide and water vapor, many scientists believe the earliest volcanoes belched out a more reducing atmosphere, rich in gases like methane, ammonia, and hydrogen sulfide. As this chemical cocktail is blasted upward, it is injected directly into the heart of the electrical storm. Here, the intense energy from volcanic lightning acts as a universal spark. It tears apart the simple gas molecules, creating a soup of highly reactive radicals and ions. In the turbulent, ash-laden environment, these fragments are forced together in countless combinations. The ash particles themselves play a critical role, not just as a source of friction for the lightning, but as solid surfaces where the newly formed molecules can stick and undergo further reactions, shielded from being broken apart again. This process would have been relentless and global. A single large eruption could have generated thousands of lightning strikes per hour, each one a miniature laboratory flash, synthesizing organic compounds across a vast volume of the atmosphere. Over millions of years, this constant, planet-wide electrical storm would have rained a steady drizzle of prebiotic molecules onto the surface below, into the oceans and onto the land. The beauty of this theory is its terrifying scale. It suggests that the very geologic violence that made the early Earth a hostile place for established life may have been the essential engine for creating life's ingredients in the first place. The planet was not just a passive container for chemistry, but an active, sparking generator of it. While deep sea vents worked in darkness and interstellar dust worked in cold silence, the volcanoes worked in spectacular, thunderous light, writing the first lines of life's recipe in flashes across the primal sky. The quiet, ordered chemistry of clay sheets offers one path to organization, but another, more fundamental form of structure may have come first. Before any genetic code could be written, life needed a container, a way to separate itself from the chaotic outside world. The lipid world hypothesis proposes that the very first complex, self-replicating systems were not built from information-carrying molecules at all, but from the walls of the house itself. This theory shifts the spotlight away from RNA and DNA to a humbler class of molecules, lipids, the fatty acids that form the membranes of every living cell today. The argument begins with a simple, observable fact. When certain types of lipids are placed in water, they do not simply dissolve, they spontaneously self-assemble. This is because one end of a lipid molecule is attracted to water while the other end repels it. To resolve this conflict, the molecules arrange themselves into perfect two-layered sheets with their water-loving heads facing out and their water-fearing tails tucked safely inside. And when these sheets are agitated, they naturally curl into closed, hollow spheres called vesicles. In an instant, you have a microscopic, self-made container, a protocell. On the early Earth, in tidal pools or geothermal ponds rich with organic material, this process would have been continuous and automatic. Countless lipid vesicles would have formed, each one a tiny, individual experiment. But a simple bag is not life. The magic of the lipid world lies in what happened next. These vesicles were not just inert bubbles, they were dynamic. They could grow by incorporating new lipid molecules from their environment, and when they reached a certain size, gentle forces like water currents or simple osmosis could cause them to divide, pinching into two daughter vesicles. Some of the chemicals trapped inside during formation would be shared between the new bubbles. This creates a primitive form of reproduction, a heredity of chemical composition. Now imagine these protocells are not all identical. Slight variations in their lipid makeup, perhaps due to different local conditions, would give them different properties. Some membranes might be more stable, allowing them to persist longer. Others might be more permeable, letting in nutrients that allow internal chemistry to proceed faster. In a population of competing vesicles, those with advantageous traits would become more numerous, a rudimentary form of natural selection acting on non-living chemistry. The lipid membrane itself could even act as a catalyst. Certain lipids or combinations of them might speed up specific chemical reactions along their inner surface, creating a feedback loop where a vesicle that accidentally makes a beneficial compound also makes more of the lipids that helped produce it, leading to its own growth and replication. This theory paints a compelling picture of a stepping stone. It suggests that the first evolutionary competition was not between genes but between simple containers. The winning vesicles were those best at gathering resources, maintaining their structure, and dividing. Only later, within the protected environment of these successful, stable bubbles, would the more delicate chemistry of RNA and proteins have had the safe harbor it needed to develop and eventually take over the informational role. The lipid world implies that life did not begin with a spark of information, but with the simple, profound act of setting a boundary, of saying, this is inside and that is out. From that first act of separation, everything else could follow. The serene chemistry of lipid vesicles and volcanic lightning was punctuated by events of unimaginable violence. From the sky fell architects of apocalypse, meteorites, and their catastrophic energy may have written its own chapter in the book of life. The theory of meteoritic impact synthesis proposes that these collisions were not merely destructive, but paradoxically creative, forging complexity in the very instant they seemed to erase it. When a massive space rock, perhaps miles across, slams into a planet at tens of thousands of miles per hour, the release of energy is beyond comprehension. For a split second at the point of impact, temperatures soar to tens of thousands of degrees, and pressures exceed those deep within the Earth's mantle. This is not an environment where delicate organic molecules survive. It is a forge that vaporizes rock and metal. Yet, in the chaotic aftermath, within the expanding fireball and the colossal plume of ejected material, conditions become strangely fertile. As the superheated vapor from the impactor and the planet's crust expands and rises, it cools with astonishing speed. This rapid quenching from stellar heat to near ambient temperatures in minutes can freeze newly formed chemical arrangements into existence. Simple molecules present in the atmosphere like carbon dioxide, nitrogen, and water vapor, or in the impacted rocks, are shattered by the shock wave and then recombine in the cooling plume as it rains back down. Laboratory experiments using high-powered lasers to simulate these fleeting conditions have shown they can produce a wide array of organic compounds, including amino acids and the nucleobases of RNA, from utterly inorganic starting materials. The impact itself becomes a universal chemical trigger, but the creativity of an impact does not end with the fireball. The colossal crater it leaves behind, often dozens or hundreds of miles wide, sets the stage for a longer, quieter act of synthesis. The crater floor, fractured and heated by the collision, can become the site of a vast, temporary hydrothermal system. Groundwater, seeping through the hot, broken rock, is superheated and circulates for thousands of years, leaching minerals and creating the same kind of warm, chemical-rich environment found at deep-sea vents. This impact-generated hydrothermal field would have been stocked with the very organic products formed in the initial plume, providing a protected basin where those molecules could further interact, link, and complexify. So a single cataclysmic event could provide both the spark of creation and the sheltered nursery for what was created. This theory dramatically reframes the role of the late heavy bombardment, a period around 4 billion years ago when the inner solar system was subjected to a relentless barrage of impact. Rather than a sterilizing hellscape that constantly reset the clock for life, it may have been a necessary, if terrifying, delivery and processing system. Each major impact could have seeded a local region with a fresh, rich supply of organics, and then immediately provided the warm, wet, mineral-rich crater to incubate them. The violence that shaped the surfaces of the young planets may have been the very hammer that struck the anvil of probiotic chemistry again and again until something finally caught. The problem of the container leads to an even deeper puzzle. A lipid vesicle can grow and divide, but to truly evolve, a system needs a way to remember and pass on successful innovations. This brings us to one of the most compelling and elegant ideas in the entire story, the RNA world. This hypothesis proposes that the first truly complex, self-replicating molecule was not a protein or a strand of DNA, but its versatile cousin, ribonucleic acid or RNA. The beauty of RNA is that it can wear two hats. Like DNA, it is a string of nucleotides, a sequence that can store genetic information, a blueprint. But unlike the relatively stable double helix of DNA, RNA is a more flexible, single-stranded molecule. This allows it to fold into intricate three-dimensional shapes, and some of those shapes can act as catalysts, speeding up chemical reactions. An RNA molecule could, in theory, be both the instruction manual and the factory that reads it. It could copy itself. In the RNA world, these jack-of-all-trades molecules were the first life forms, replicating and competing in a primordial sea, evolving through natural selection long before the first cell or protein ever existed. Laboratory experiments have shown that under the right conditions, RNA strands can indeed catalyze the formation of new RNA strands, lending powerful support to this idea. Yet for all its elegance, the RNA world faces a monumental hurdle. RNA is a fantastically complex molecule to build from scratch. Its nucleotide building blocks are themselves intricate assemblies of a sugar, a phosphate, and a nucleobase. Getting these pieces to form spontaneously in probiotic conditions and then linked together into long, functional chains is a chemical challenge of staggering difficulty. The conditions that might form the sugars can destroy the nucleobases and vice versa. It is like trying to bake a cake in an oven that keeps randomly switching between broiling and freezing. This has led many scientists to suspect that RNA was not the starting point, but an evolutionary upgrade. Perhaps the first genetic molecules were something simpler, something more robust that could form more readily on the early Earth or in space. These are the hypothesized predecessors, the molecular prototypes. One leading candidate is called peptide nucleic acid, or PNA. Imagine taking the backbone of RNA, that alternating chain of sugar and phosphate, and replacing it with something far sturdier, a backbone made of linked amino acids, the same simple building blocks that form proteins. This PNA molecule can still pair with RNA or DNA, meaning it can carry the same kind of genetic information, but its structure is more resistant to heat and chemical breakdown. It is a simpler, tougher candidate for the first information-carrying polymer. Another prototype is threose nucleic acid, or TNA. Here, the sugar in the backbone is different. RNA uses ribose, a 5-carbon sugar that is notoriously fragile. TNA uses threose, a sugar with only 4 carbons. This smaller sugar is chemically more stable, and crucially, experiments suggest it can form more easily under prebiotic conditions. TNA can also form double helices and can even transfer information to and from RNA, acting as a potential evolutionary bridge. The profound implication of these precursor theories is that the path to life may have been a stepwise molecular evolution. First, geology and chemistry produced simple, hardy molecules like PNA or TNA in tidal pools or on clay surfaces. These prototypes began the process of replication and selection. Over time, through countless chemical experiments, a more efficient but more delicate molecule, RNA, eventually evolved within this molecular ecosystem, later teaming up with lipids for containment and proteins for better catalysis. The RNA world might not have been the first world, but the second, inheriting its genetic logic from a humbler, hardier ancestor. This shifts the search from a single miraculous molecule to a cascade of chemical innovations, each building on the last. If life's first information system was a crude prototype, what raw energy source kept its primitive machinery running? The silent chemistry of cold dust grains holds one more secret, a trigger more precise than a cosmic ray. Deep within the icy mantles coating those microscopic specks, specific photons from distant stars act as molecular sculptors. This is not a blunt force, but a delicate operation. Ultraviolet light, carrying just the right amount of energy, does not simply warm the ice. It can be absorbed by a single frozen water or carbon monoxide molecule, exciting it to a breaking point. The photon's energy severs a specific chemical bond with surgical precision, creating a pair of highly reactive fragments called radicals. These radicals are now trapped, frozen in place beside each other in the rigid ice matrix, charged with potential but unable to move. They are prisoners in a crystal cage. The story changes when the environment shifts, as a molecular cloud begins to collapse under its own gravity. Destined to become a new solar system, it does not heat evenly. Gentle warming pulses through the cloud, perhaps from the shockwave of a nearby star's birth or the simple compression of the gas. This warming is slight, only a few tens of degrees, but it is enough to soften the icy mantle. The rigid crystal lattice of the ice becomes more pliable, allowing the trapped radicals a tiny amount of movement. Now, the fragments created by that ancient ultraviolet photon are no longer frozen in isolation. They can shuffle just a few atomic distances and find each other. When they meet, they combine in an instant, forming a new, more complex molecule that never could have assembled through random collisions in the gas. This two-step process, photon breaking followed by thermal merging, is incredibly efficient. It allows for the buildup of molecules that require very specific, high-energy bonds to form initially, but which are then locked into a stable form as the ice warms. Laboratory experiments simulating these conditions have shown this can produce molecules like glycolaldehyde, a simple sugar, and ethylene glycol, directly from ices of carbon monoxide and hydrogen. The gentle warming acts like a cosmic timer, deciding exactly when the radicals created by starlight eons ago will finally be allowed to finish their reaction. This means the inventory of organic molecules in a newborn planetary system could be pre-programmed by the specific history of starlight its parent cloud experienced. The collapsing cloud is not just gathering material, it is gently thawing a frozen library of chemical potential written by the galaxy's light. So the first complex molecules in a new solar system might not be forged in its fiery center, but patiently assembled in the dark frost of its outskirts, waiting for the moment a little warmth would tell them it was time to become something new. Deep beneath the ocean, in the absence of sunlight, life still found a way to tap into energy. But what if the first complex molecules were born not in the dark, but in the light, using a mineral that acted like a primitive solar panel? This is the zinc sulfide world hypothesis, a niche but fascinating idea that gives the deep sea vent a surprising new twist. The star of this theory is a common mineral, zinc sulfide, often found as the brassy-looking ore called sphalerite. Near the hydrothermal vents on the early ocean floor, this mineral would have precipitated out of the hot, mineral-rich fluids, forming crusts and, crucially, porous, sponge-like structures. To our eyes, it is just a rock, but to a chemist, it is a semiconductor, a material that can absorb light and use that energy to drive chemical reactions. The early Earth's surface was bathed in intense ultraviolet light from the young sun, light that would have penetrated the upper layers of the ocean. Even at the depths of hydrothermal vents, there would have been a faint, persistent glow, not from the sun, but from the vent fluids themselves, which can emit a soft light from thermal radiation and chemical reactions. This is where the magic happens. A porous zinc sulfide crust, sitting at the interface between the hot vent fluid and the cooler seawater, becomes a tiny, efficient factory. When a photon of light, whether from above or from the vent's own glow, strikes the zinc sulfide crystal, it energizes it. This energy knocks an electron loose, creating a positively charged hole. These separated charges are desperate to recombine, and they will use any available molecule to do so. On the mineral's vast porous surface, simple gases bubbling up from the vent, like carbon dioxide and hydrogen sulfide, are absorbed. The energized zinc sulfide uses its loose electrons and holes to rip these simple molecules apart and reassemble them. In a series of steps called redox reactions, the carbon dioxide is reduced, gaining electrons to become more hydrogen-rich, while the hydrogen sulfide is oxidized, losing electrons. The products are the building blocks of life, organic molecules like formic acid, formaldehyde, and more complex chains. This process is a beautiful two-for-one deal. The zinc sulfide mineral does not just provide a surface for the reaction, it provides the very energy that powers it, harvested directly from ambient light. It acts as both catalyst and battery. The porous structure is key, creating an enormous surface area where gases can be trapped and reactions can occur in countless tiny chambers, all simultaneously humming with photochemical activity. This theory suggests a seamless bridge between the chemical energy of the vent and the radiant energy of the sun. A single mineral scaffold, sitting in a dynamic, nutrient-rich flow, could have continuously churned out organic feedstock driven by a gentle, ubiquitous glow. It turns a rocky crust into an ancient, inorganic metabolism, a steady producer of complexity that required no lightning, no impact, just the quiet, persistent physics of light meeting stone. If such a simple mineral could act as a proto-metabolism, what other common substance might have held the power of selection to choose which molecules thrived and which faded away? The faint sweetness of life may have been written in the stars long before it touched a planet. Deep within the swirling chaos of star-forming regions, radio telescopes have picked up the unmistakable chemical signature of a molecule called glycolaldehyde. It is the simplest possible sugar molecule, just 8 atoms of carbon, hydrogen, and oxygen arranged in a tiny, sweet chain. Its discovery in interstellar space is not just a curious fact, it is a profound clue. Glycolaldehyde is far more than space candy. It is a chemical stepping stone of immense potential, a universal intermediate that could have bridged the gap between cosmic chemistry and the molecules of life. In the cold, dark clouds where it forms, likely through those gentle processes of surface chemistry on dust grains, glycolaldehyde is a patient reagent. It does not simply sit still. When it encounters other simple molecules that are also abundant in those clouds, like formaldehyde, a remarkable cascade can begin. Through a series of reactions known as the foremost pathway, these simple sugars can link together, growing in complexity. Under the right conditions, with just a little energy or the right mineral catalyst, glycolaldehyde can be the seed from which larger sugars emerge. Most tantalizing of all, this process can lead to the formation of ribose, the precise 5-carbon sugar that forms the structural backbone of every molecule of RNA, the hypothesized pioneer of genetics in the RNA world. Think of it as a cosmic assembly line already preset to produce a critical component. The raw carbon, oxygen, and hydrogen are floating everywhere. The cold surfaces of dust grains provide the workbench. And the basic chemical rules of attraction and bonding do the rest slowly over millions of years, building from 2-carbon glycolaldehyde to 3-carbon sugars, and eventually to the 5-carbon ribose. This theory suggests a staggering possibility. The sugar half of RNA's building blocks did not have to be invented on Earth. It was already being manufactured in the molecular cloud that gave birth to our solar system, frozen into the ice of comets and asteroids and delivered here as a finished product. The implications are dizzying. It means the recipe for life's informational molecule was not a local secret, but a galactic commonplace. Anywhere in the universe where stars are born from similar clouds of gas and dust, this same sugary chemistry could be unfolding, stocking nascent planetary systems with the same sweet set of ingredients. The universe, it seems, has a sweet tooth for complexity. If the sugars were raining down from space, ready-made, what about the other half of the recipe, the information-carrying nucleobases? Could they too have been part of the same cosmic delivery? The transition from isolated molecules to a sustained chemical system requires a steady flow of energy and materials, a primitive metabolism. This brings us to a hypothesis that finds the blueprint for life's first engine not in an organic molecule, but in a common mineral. The iron-sulfur world theory suggests the very first metabolic cycles were not biological at all, but geological, running on the catalytic power of fool's gold. At the heart of this idea is a simple but profound observation. Deep within the proteins that power every living cell's metabolism, at their reactive core, you often find tiny, intricate clusters of iron and sulfur atoms. These are not accidental contaminants. They are the ancient functional heart of the enzyme, the part that actually performs the chemistry. The iron-sulfur world asks a revolutionary question. What if these metal clusters came first, and biology later built its sophisticated machinery around them? Imagine the scene at a hydrothermal vent. Superheated, mineral-rich water surges from the seafloor, rich in dissolved hydrogen sulfide and iron ions. As this fluid meets the cold ocean water, it precipitates out, forming porous, chimney-like structures made of iron sulfide minerals like pyrite and maconite. These are not smooth, inert rocks. Their surfaces are a ragged landscape of reactive sites, with iron and sulfur atoms left with unsatisfied bonds, eager to interact with passing molecules. Now picture simple gases bubbling through this mineral labyrinth, carbon dioxide and hydrogen, both readily available from vent chemistry. The iron-sulfur surface acts as a catalyst, a solid-state enzyme. It grabs hold of the carbon dioxide and hydrogen molecules, using the unique electronic properties of the iron-sulfur cluster to weaken their bonds and force them to rearrange. In a stepwise process, the mineral surface facilitates the reduction of carbon dioxide, stripping away oxygen atoms and adding hydrogens. This is not a random event, it is a directed chemical pathway. The reaction releases a small amount of energy, and more importantly, it produces simple organic molecules like formic acid or acetic acid. This is carbon fixation, the fundamental act of taking inorganic carbon and building it into an organic backbone, and it is happening without a single protein or strand of RNA. The beauty of this system is its self-sustaining nature. The iron-sulfur mineral is not consumed, it is a persistent, reusable platform. The reactions it catalyzes release enough energy to potentially drive other linked processes, creating a network, a cycle. One product of a reaction could become the feedstock for the next, all orchestrated on the conductive, catalytic surface of the mineral. This creates a proto-metabolism, a sustained chemical flow that generates both building blocks and usable energy in one integrated package. It is a metabolism in stone. The theory proposes that these mineral-catalyzed cycles in vent environments were the training ground for organic chemistry. Over time, organic molecules that formed in this flow might have started to associate with the mineral surfaces, eventually forming organic coatings that improved the efficiency of the reactions. Eventually, through a process of molecular evolution, the organic components could have taken over the catalytic role, with the original iron-sulfur clusters remaining at the center as a relic of their geological origin. So the iron-sulfur world does not just offer a place for life's ingredients to form, it offers a reason, a primal driver. It suggests that metabolism, the relentless churn of energy and matter that defines life, may have begun as a whisper in the rocks, a geochemical hum that the first biological cells learned to amplify and call their own. The rhythmic pulse of the ocean offers a different kind of energy, not from heat or light, but from patience and repetition. Along the rugged coastlines of a young Earth, tidal pools and the edges of geothermal hot springs became nature's most reliable chemical workshops. Here, the theory suggests the crucial leap from small organic molecules to long, information-capable chains was driven by something as simple as the tide going out. Imagine a shallow, rocky basin filled with water rich in the scattered organic building blocks delivered by comets or synthesized by volcanoes. This broth is far too dilute for the molecules to find each other and link up. They are like people in a vast, empty stadium, unlikely to ever meet. But then the sun beats down or the hot spring's heat does its work and the water begins to evaporate. As the water level drops, everything dissolved within it becomes dramatically more concentrated. Amino acids, nucleotides, and other monomers are forced into ever closer proximity, no longer drifting in a vast sea, but crowded together on the shrinking film of liquid coating the rocks and sediments below. This concentration is the first critical step. Now, the mineral surfaces lining the pool, clays or volcanic rocks, come into play. As the last of the water evaporates, these molecules are not just clothes, they are pressed directly onto these mineral templates. They are immobilized, aligned, and held in perfect orientation for a reaction, much like beads arranged on a string. The final, vital ingredient is the act of dehydration itself. Linking two amino acids to form a peptide or two nucleotides to form a strand of nucleic acid requires the removal of a water molecule. In a constantly wet environment, this is chemically difficult. It is like trying to glue something together underwater. But in a drying tidal pool, the environment itself is doing the work, constantly removing water and thereby pushing the equilibrium toward bond formation. The energy of the sun or geothermal heat provides the gentle nudge needed to overcome the final barrier. Each cycle, wet then dry, acts like a single turn of a chemical crank. When the tide returns or rainwater refills the pool, it brings a fresh supply of monomers and dissolves the newly formed polymers, protecting them from being broken down by the same dry heat that created them. Over countless cycles, days turning to years turning to millennia, these short chains could have linked together into longer and longer polymers. A peptide a few units long formed in one dry phase might, in the next cycle, link with another, gradually building up to proteins capable of simple catalysis. Nucleotides aligned on a clay surface could have polymerized into RNA-like strands long enough to fold and perhaps even carry a whisper of information. This setting is compelling because it is so universal and inevitable on any rocky world with liquid water and a tidal force, whether from a moon or planetary rotation. It requires no extraordinary event, just the patient cyclical rhythm of the planet itself, concentrating, aligning, and dehydrating over and over, turning a dilute probiotic soup into a rich polymer library one tide at a time. This preference is a signature written into every living thing, Amino acids, the building blocks of proteins, come in two mirror image forms, left-handed and right-handed, a property called chirality. In the non-living world, chemical reactions produce a perfect 50-50 mix of both forms. Yet life, from the simplest bacterium to the most complex human, uses exclusively left-handed amino acids and right-handed sugars. This universal bias, known as homochirality, is one of the most profound and unsolved mysteries in the story of life's origins. How could a random, abiotic process lead to such a perfect, one-handed selection? The answer may lie in forces that acted as a cosmic filter, tipping the scales before biology even began. One compelling idea points to the heavens, to the violent death throes of massive stars. When certain stars collapse into rapidly spinning neutron stars, they can emit a peculiar form of light called circularly polarized light. Unlike ordinary light, which vibrates in all directions, this light spirals like a corkscrew, twisting either to the left or to the right as it travels through space. This spiral light could have acted as a universal chiral selector. As this polarized starlight bathed the molecular clouds and dust grains where prebiotic molecules were forming, it would not have affected both mirror image forms equally. The spiraling photons would have interacted more strongly with one-handedness, selectively breaking down and destroying those molecules over time. Imagine a vineyard where a persistent wind blows only from the east, consistently knocking ripe grapes from the vines on one side of the row. Over many seasons, the harvest would become overwhelmingly skewed. In a similar way, over millions of years, the relentless, one-handed light from neutron stars could have filtered the primordial organic inventory, leaving behind an excess of the molecular handedness that life would later adopt. This process would have imprinted a chiral bias across entire regions of the galaxy, making the selection not a local accident but a celestial inevitability. Closer to home, the geology of the early Earth may have provided its own selective surface. Certain common minerals, like quartz crystals, are themselves chiral. Their atomic structure forms in a left-handed or right-handed spiral. When a solution containing a 50-50 mix of amino acids washes over a bed of, say, right-handed quartz crystals, the surface does not treat both forms identically. One mirror image form will fit more snugly onto the crystal's spiral grooves, like a hand slipping into a perfectly shaped glove. This preferential adsorption does more than just gather molecules, it can also catalyze their formation. Chemical reactions happening on that templating surface would be more likely to produce the amino acid that matches the mineral's own handedness. A left-handed quartz surface would template left-handed amino acids, and a right-handed surface would template right-handed ones. On a planet with vast, uneven deposits of these minerals, one chiral form could have gained a tremendous local advantage, creating regional reservoirs of molecular handedness. Once this initial bias was established, even a small imbalance could have been amplified through subsequent chemical cycles, like an avalanche started by a single stone. The chiral purity of life, therefore, might not be a biological choice but a geological memory, a frozen echo of the crystalline landscapes where its molecules first learned to assemble. This fundamental selection, whether written by starlight or stone, set a precedent that every living organism would inherit, a unified direction for the chemistry of life that persists across the entire tree of life. If the very handedness of our molecules was decided by ancient crystals or distant stars, what other invisible templates might have guided the next critical step, the emergence of something that could not just be, but do? Our own planet's ancient atmosphere is lost to time, but a living relic of that era orbits Saturn. Titan, shrouded in a thick orange haze, offers a stunning glimpse into a chemical pathway that could have been vital on countless worlds. This moon's dense atmosphere is primarily nitrogen, with a few percent methane, a mix eerily reminiscent of what scientists suspect cloaked the young Earth and Mars. Under the relentless bombardment of solar ultraviolet light, This simple atmospheric cocktail undergoes a profound transformation. High in Titan's sky, ultraviolet photons break apart methane and nitrogen molecules, creating a soup of highly reactive radicals. These fragments link together in a dizzying cascade of reactions, building larger and more complex hydrocarbons and nitriles. The end products are not simple gases, but large, complex organic polymers that condense into fine, orange-colored particles. We call these tholins from the Greek word for muddy. This photochemical smog is so thick it perpetually hides Titan's surface from view, but the process does not stop in the sky. These tholin particles are heavy. They slowly drift down through the dense atmosphere, creating a constant, gentle organic rain. On Titan, this rain falls not onto water oceans, but onto a frigid landscape dotted with lakes and rivers of liquid methane and ethane. Here, in these alien solvents, the tholins may undergo a second act of chemistry. Dissolved, concentrated, and perhaps interacting with the lakebed sediments or occasional cryovolcanic heat, these pre-made complex molecules could react further, assembling into an even richer diversity of compounds. This entire system, from atmospheric synthesis to surface deposition, is a self-contained, planet-wide factory for probiotic material. The theory of atmospheric photochemistry suggests that early Earth, with a similar nitrogen-methane cloak, would have operated in much the same way, but with one critical difference. Instead of raining into methane lakes, the organic haze would have showered down into warm, global oceans of water. The tholins, or their terrestrial equivalents, would have dissolved, creating a concentrated organic broth in the surface waters and shorelines. This provides an elegant solution to the dilution problem, a steady, top-down delivery of complexity that could enrich the primordial soup far more efficiently than undersea vents or rare impacts alone. Titan stands as a colossal natural laboratory, demonstrating that given the right atmospheric ingredients and an energy source as universal as starlight, the universe can spontaneously paint entire worlds with the tarry brushstrokes of complex organic chemistry. It shows us that the path to life's ingredients might not require a special, sheltered niche, but could instead be written across the sky of any suitable world, raining its potential down from the heavens themselves. But perhaps the most secluded cradle of all lies not in the ocean or the sky, but in the stone itself. Miles beneath the chaotic surface of the early Earth, shielded from asteroid impacts and searing ultraviolet light, another kind of chemistry was stirring in the perpetual dark. This is the deep biosphere lithoeutotroph theory, and it suggests life's first complex molecules were forged in the crushing pressure and total isolation of the planet's own crust. Today, we find entire ecosystems thriving in this unimaginable environment. Microbes called lithoeutotrophs, literally rock self-feeders, survive with no sunlight or organic food from the surface. Their secret is geochemical energy. They get all the sustenance they need from the simple act of water reacting with certain kinds of rock, a process called serpentinization. When water seeps down through cracks and encounters minerals like olivine, a common component of the Earth's mantle, a slow, powerful reaction begins. The rock is altered, transforming into a green, serpentine mineral. But more importantly, the reaction releases hydrogen gas and generates heat. For a microbe, this is a feast. It can use that hydrogen, along with carbon dioxide also dissolved in the water, as fuel to build its own organic molecules from scratch. This is a complete, self-contained metabolic engine running on geology alone. The theory proposes that the ancestors of these modern microbes were not just living down there, they were born there. In the earliest chapters of Earth's history, the crust was still cooling and fractured, allowing water to penetrate to great depths. In these sunless, high-pressure aquifers, the serpentinization reaction would have been widespread and continuous, creating vast, interconnected networks of warm, hydrogen-rich fluids. Within this stable, protected realm, the conditions were perfect for sustained chemistry. The constant flow of hydrogen and carbon dioxide over the catalytic surfaces of freshly fractured minerals could have driven the stepwise formation of increasingly complex organic molecules. There were no destructive surface cycles here, no drying or freezing, just a steady, warm, energy-rich flow that could have persisted for millions of years, completely undisturbed by the apocalyptic violence happening far above. The deep crust was more than a shelter, it was an independent point of origin. It presents the possibility that the journey from geochemistry to biochemistry did not require a sunny tidal pool or a volcanic sky, but could have begun in the planet's own subterranean heart, a genesis in the dark that later, when conditions calmed, seeded the surface world above. This idea forces us to reconsider where to look for life's beginnings, not just on our world but on others. If the first complex systems can arise in the absolute isolation of a planet's deep rock, then the habitable zone for life in the universe expands from the narrow band around a star to include the inner depths of countless frozen or barren-seeming worlds. The cradle of life may not have been a cradle at all, but a vault locked deep within the stone where chemistry patiently worked in secret until the world was finally ready. The frozen heart of a comet is far more than a simple ice ball. It is a stratified archive, a layered record of the solar system's birth, and according to this theory, it may also have been a traveling chemical factory. While panspermia paints comets as passive couriers, the cometary factory model suggests they were dynamic reactors, actively upgrading their own organic cargo over eons. A comet's nucleus is not uniform. Think of it as a cosmic onion, or more accurately, a dirty snowball with distinct geological layers. It contains a mix of ices, water, carbon dioxide, methane, and ammonia, all intimately mixed with dust grains of silicate rock and complex carbonaceous material. For most of its long, elliptical orbit, this conglomerate sleeps in the deep freeze of the outer solar system. But when its path swings it close to the sun, everything changes. Solar heating does not simply vaporize the surface ice in a uniform blast. Because the ices have different volatility, they sublimate at different rates and temperatures. This uneven heating, combined with the comet's often irregular rotation, creates a complex internal thermal landscape. Calculations and data from missions like the European Space Agency's Rosetta probe suggest a fascinating possibility. In certain regions, beneath an insulating crust of dust and less volatile material, the heat from the sun could penetrate just deeply enough to melt some of the water ice, rather than instantly vaporizing it. This would create transient, localized pockets of liquid water trapped within the comet's own body. These pockets would be tiny, perhaps no larger than a household room, and they would be fleeting, lasting only weeks or months during the comet's brief perihelion passage. But for chemistry, that is an eternity. Within these sheltered, liquid microenvironments, the conditions become astonishingly fertile. The water is not pure. It is a briny soup, rich with all the minerals and simple organic compounds that were frozen into the comet's matrix since its formation. Suddenly, molecules that have been frozen in place, millimeters apart but chemically isolated for billions of years, are now dissolved and mobile. They are concentrated, forced into constant contact. The warmth provides the activation energy, and the surrounding ice and rock provide both a container and a catalytic surface. In this temporary pocket, the same kinds of chemical reactions we have discussed, the linking of amino acids or the formation of nucleobases, could proceed at a vastly accelerated pace. A single comet might experience thousands of these heating cycles over its lifetime. Each close pass to the sun could create new liquid pockets in different regions, each one a fresh experiment in probiotic synthesis. Over millions of years, a comet would not just preserve its primordial organics, it would actively process them, cooking its initial simple inventory into a richer, more diverse suite of complex molecules. Then, when a jet of gas erupts from its surface, it does not just release pristine ancient ice. it could be spraying out a mist of newly minted, biologically relevant compounds. This transforms our view of comet delivery. It is no longer a simple transfer of raw materials from point A to point B. It is the delivery of a pre-processed, refined chemical toolkit. A comet impacting the early Earth would not just be bringing the basic alphabet of life, but perhaps whole paragraphs, molecules that had already undergone significant steps toward complexity in the solitude of space. The factory was mobile, its production cycles tied to the rhythms of its orbit, quietly upgrading the universe's chemical potential one close solar pass at a time. Acetylene is the universe's welding torch, a tiny molecule of two carbon atoms triple bonded together, surrounded by hydrogen. It burns with a brilliant, sooty flame on Earth, and it drifts through the atmospheres of gas giants and the cold of interstellar space. This deceptively simple hydrocarbon might have been another master key, offering a robust and surprisingly direct route to life's genetic code. The acetylene-based pathway theory explores how this energetic little molecule, under the right guidance, could have snapped together the ring-shaped structures essential for storing biological information. At the heart of this idea are reactions that feel almost industrial in their simplicity. In the haze of a young planetary atmosphere, perhaps on a world like Titan or early Earth, acetylene would have been a common product. Ultraviolet light breaking down methane or the intense heat of volcanic plumes could have produced it in abundance, but acetylene is not very reactive on its own in these environments. It is a stable, linear molecule. It needs a matchmaker, a catalyst to unlock its potential. This is where common cosmic metals come in. Imagine microscopic flecks of nickel or iron, perhaps floating as dust or embedded in the surface of a mineral. These metals have a special ability to grab onto acetylene molecules and hold them in a precise, strained configuration. Once activated by this metallic handshake, the acetylene becomes primed for connection. Now, introduce a nitrogen source, something as universal as ammonia or hydrogen cyanide, also plentiful in those early atmospheres and in space. The catalyzed acetylene can react with these nitrogen compounds in a series of steps that seem almost destined to form a pyrimidine, one of the two families of nucleobases that make up DNA and RNA. Specifically, laboratory experiments have shown that under plausible probiotic conditions, this metal-catalyzed pathway can lead to the formation of cytosine, a critical letter in the genetic alphabet. Think of it as a three-ingredient recipe: acetylene, nitrogen, and a metallic dust, coming together under the gentle warmth of a planetary surface or the energy of atmospheric lightning to build a fundamental component of heredity from scratch. But acetylene's versatility does not end there. In a different setting, perhaps in a warm subsurface aquifer or a tidal pool, the same activated acetylene could take a different fork in the road. Instead of reacting with nitrogen, it could interact with liquid water in the presence of a catalyst. This hydrolysis reaction would transform the acetylene into reactive aldehydes like acetaldehyde. These aldehydes are not just random products, they are themselves fantastic springboards for further chemistry. They can readily undergo reactions to form sugars, amino acids, and other multi-carbon backbones. So from one simple starting molecule, acetylene, the universe had multiple robust pathways, one leading directly to the information-carrying rings of genetics, and another feeding into the vast network of metabolic and structural molecules. This theory's power lies in its raw materials and conditions. Acetylene is simple and widespread. Nickel and iron are among the most common metals in the cosmos, found in meteorites and planetary crusts. The needed nitrogen compounds are ubiquitous. It does not require a rare, special environment, but could have operated in the atmospheres of various planetary types, in impact plumes, or even on the surfaces of asteroids warmed by radioactive decay. It presents a universe that is not just stocked with organic parts, but one wired with efficient chemical circuits, ready to assemble those parts into ever greater complexity wherever the most common elements and a bit of energy coincide. If such a straightforward reaction could forge a nuclear base, what other common cosmic molecule might have held a similar, hidden potential for creation? The rules of chemistry we take for granted may only be half the story. At the most fundamental level, where molecules are built and bonds are broken, the bizarre laws of quantum mechanics reign. A radical new idea suggests these quantum effects were not just present at life's dawn, they were essential architects guiding chemistry with a subtle, invisible hand. This is the theory of quantum coherence in probiotic chemistry. We have already seen how quantum tunneling allows reactions like hydrogen atom addition to occur in the deep cold of space, where classical chemistry says they should be frozen solid. But tunneling is just the beginning, a simple quantum trick. The more profound concept is quantum coherence. In our everyday world, objects have definite properties and locations. In the quantum realm, particles like electrons exist in a haze of possibilities, a superposition of states until they are observed or interact with their environment. When this delicate, wave-like state is maintained across a system, it is called coherence. For a fleeting moment, a molecule or a set of molecules can explore multiple chemical pathways simultaneously, almost as if testing them out before settling on the most efficient route. Imagine a single photon of light, perhaps from the young sun, striking a cluster of simple molecules on a wet clay surface or within a porous mineral. Classically, that energy would be absorbed by one molecule, causing it to vibrate and heat up, with the energy dissipating as waste heat. But in a coherent quantum system, something else can happen. The energy does not localize. Instead, it exists as a shared wave of excitation across the entire molecular cluster. This quantum coherence allows the energy to flow without loss, like a perfectly tuned chord resonating through a crystal, searching for the perfect site to trigger a chemical reaction. It could guide that precious packet of energy directly to the exact bond that needs to be broken or formed, with nearly 100% efficiency. This is not random chemistry, it is directed chemistry. The system itself, through quantum interference, selects the fastest, most effective pathway from a multitude of possibilities. In the noisy, wet, warm environment of a tidal pool or a vent, such delicate quantum states would be destroyed almost instantly, a process called decoherence. But in the cold, ordered structures of interstellar ice mantles, or within the rigid, crystalline lattices of certain minerals, coherence could persist long enough to matter. A mineral like fool's gold, with its repeating iron-sulfur clusters, could have provided the perfect quantum playground, its structure maintaining coherence long enough to orchestrate the precise electron transfers needed to reduce carbon dioxide into organic molecules. This theory moves us from a universe of chance collisions to one of subtle orchestration. It proposes that the first steps toward complexity were not just a chemical lottery, but a quantum-assisted search for efficiency, written into the fabric of reality itself. The molecules of life may have found their form not in spite of the quantum world, but because of it, following a ghostly blueprint of probability and interference toward the most stable, productive arrangements. The universe's first complex molecules might not have been delicate chains or rings, but something far stardustier. Drifting through the void, woven into the fabric of nebulae and comets, are vast clouds of polycyclic aromatic hydrocarbons. These are not mere specks of dust, but large, flat, and incredibly stable molecules built from interlocking rings of carbon and hydrogen. They are essentially the sooty skeletons of cosmic fires, the molecular ash left over from dying stars. The PRH world hypothesis suggests these resilient carbon scaffolds were not just space junk. They were the universe's first stable workbenches, providing a fundamental platform upon which the delicate chemistry of life could finally gain a foothold. Imagine a single PRH molecule as a microscopic tile, a hexagon of carbon atoms with a perfect geometric surface. In the chaotic chemical soup of a young planet or a comet's interior, this tile offers something precious: order. Its flat, wide surface is hydrophobic, meaning it repels water. In a watery environment, this creates a powerful organizing force. Other organic molecules that are also water-averse, like certain lipids or nuclear-based precursors, would be naturally drawn to stick to this stable, dry island. The pH does not just gather them, it aligns them. Lying flat on that carbon surface, these gathered molecules are held in close, orderly proximity, perfectly positioned to react with one another. The pH acts as a non-stick pan that somehow makes the ingredients want to combine, but its role goes beyond simple templates. These molecules are also exceptional energy sinks. When struck by ultraviolet light from the young sun or the energy of a cosmic ray, a pH does not simply shatter. Its ringed structure is so robust it can absorb that energy and re-emit it as a gentler, more usable form, like heat or even a faint guiding fluorescence. In a primordial setting, a cluster of pH molecules could have acted as a protective energy buffer, soaking up destructive high-energy radiation and dissipating it in a way that warmed and energized the local chemical environment without obliterating the fragile new molecules assembling on their surfaces. Some researchers even propose these stacks could have formed primitive light harvesting systems, akin to the chlorophyll in plants, capturing photons and using that energy to drive the very reactions that build complexity. Perhaps most intriguing is their structural potential. pH molecules do not like to float alone. Their flat shapes make them want to stack together, like a deck of cards or the pages of a book. These stacks could have created layered corridors, sheltered spaces between the carbon sheets where other molecules could be protected, concentrated, and guided into specific three-dimensional arrangements. This stacking might have been a crude precursor to the layered structures of clays, but made from organic carbon itself. In this view, PHS provided the first durable, all-organic infrastructure. They were the stable docks in the chaotic probiotic sea, the platforms that gathered the scattered tools, the shelters that protected them, and even the batteries that powered their assembly. Before genetic code or cellular membranes, the universe may have relied on these sooty, silent tiles of carbon, woven in stellar furnaces, to give chemistry the stable foundation it needed to build something entirely new. Energy is the universal currency of change, and life needed a way to spend it. While theories of genetic templates and lipid containers show us where information and structure could have come from, they leave a fundamental question unanswered. What powered the assembly line? The Thioester world hypothesis offers a compelling answer, suggesting that before there was a genetic code to read, there was a simple, powerful molecule that acted as life's first battery, plugging directly into the planet's own geochemical grid. This theory focuses on a class of compounds called thioesters, molecules where a carbon atom is linked to a sulfur atom through a high-energy bond. In every living cell today, thioesters are still the workhorses of metabolism. The most famous is acetyl coenzyme A, the central hub that fuels the Krebs cycle, the process that generates energy in our mitochondria. The fact that this ancient energy-carrying structure is still at the core of all modern biochemistry is a powerful clue that it might be a fossil of life's very first engine. So how could these crucial molecules have formed without any biology to make them? The answer lies once again in the dynamic chemistry of the early Earth, particularly around sulfur-rich environments like hydrothermal vents. Here, superheated water laden with dissolved minerals like iron sulfide and hydrogen sulfide gushes from the seafloor. In this chaotic mix, simple, abundant molecules like acetic acid, which could have formed from volcanic gases or deep-sea reactions, could have readily combined with hydrogen sulfide. The result would be a simple thioester, a tiny packet of chemical potential energy. The bond between the carbon and sulfur in a thioester is special. It is like a coiled spring, holding a significant amount of energy that is released when the bond is broken. This released energy is not wasted as heat. It can be directly captured and used to do chemical work. In the prebiotic world, that work was likely condensation polymerization, the crucial process of linking small molecules into long chains by removing a water molecule. Imagine amino acids or nucleotides floating in the vent's warm waters. On their own, they are stable and unlikely to link up because forming that new bond requires an input of energy and the ejection of a water molecule. But in the presence of thioesters, everything changes. A thioester could have acted as a chemical middleman. It could have reacted with, say, an amino acid, temporarily forming a high-energy, activated version of that molecule. This activated amino acid is now primed and desperate to get rid of its extra energy. When it bumps into another amino acid, it readily transfers that energy into forming a new peptide bond, linking the two together and releasing the thioester's sulfur component as a byproduct. This process could have repeated, driven by a steady, abiotic supply of fresh thioesters from the vent chemistry, building longer and longer chains without any guiding template or enzyme. The vent environment provides the perfect setting for this, a continuous flow of both the raw building blocks and the energy currency to assemble them. The thioester world proposes a profound sequence of events. First, geochemistry produces a simple, energy-rich molecule. Second, that molecule's inherent reactivity drives the formation of the first polymers. Third, these polymers, perhaps some with weak catalytic abilities, begin to interact with and improve the efficiency of the thioester-driven reactions. In this view, metabolism, the relentless flow and transformation of energy and matter, came first. It was a self-sustaining chemical whirlpool powered by geology that accidentally began to spin off complex organic products. Genetics and replication could have evolved later as a way to record and stabilize the most successful metabolic patterns. This idea turns the narrative inside out. It suggests life did not begin with a molecule trying to copy itself, but with a system learning to harness a planetary energy source, building complexity one energized link at a time, driven by the simple, sulfurous spark of a thioester bond. This faint, omnipresent glow saturates the entire cosmos. It is the cosmic microwave background, the cooled and stretched afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. Today, it bathes every cubic inch of space in a sea of microwaves, a uniform whisper at a temperature of just 2.7 degrees above absolute zero. For decades, it has been a treasure map for cosmologists, revealing the infant universe's structure. But a radical, almost poetic theory asks if it did something more, if this primordial light was not just a passive observer, but an active participant in the story of complexity. Could this universal hum have acted as a subtle catalyst, tuning the very first chemical reactions? The idea hinges on resonance, a concept as familiar as a singer shattering a glass with the right note. Every molecule vibrates and rotates at specific, quantized frequencies. To shift from one energy state to another, a molecule must absorb a photon of light with precisely the right energy, a perfect match. The cosmic microwave background is not a single frequency, but a blackbody spectrum, a smooth curve of radiation peaking in the microwave range. Within that curve are countless photons, each with a specific energy. The theory proposes that in the sparsely populated early universe before stars flooded space with their own light, this background radiation was the dominant energy field. Its specific temperature meant its photon energies corresponded to the cold, slow world of molecular clouds. Perhaps, just perhaps, the peak energy of this ancient light resonated with the rotational or vibrational transitions of certain key prebiotic molecules or their precursors. Imagine a simple molecule like hydrogen, cyanide, or water drifting in the dark of a protogalaxy. A photon from the cosmic microwave background, a relic from the birth of everything, strikes it. If the energy is just right, it is absorbed not to break the molecule apart, but to gently excite it, to push it into a slightly higher energy state that makes it more reactive, more likely to form a new bond with the next atom it encounters. This would not be a dramatic forging in fire, but a gentle, universal nudge, a whisper of encouragement from the cosmos itself, favoring the formation of specific molecular arrangements over others. The most profound implication may concern chirality, the handedness of life's molecules. Some scientists speculate that the circular polarization patterns imprinted on the cosmic microwave background by the earliest structures in the universe could have been asymmetrical. If these polarized photons interacted differentially with left and right-handed molecular forms, even with an infinitesimally small bias, that universal filter could have set the chiral preference for every galaxy, or even the entire observable universe from the very beginning. It is a staggering thought that the faint echo of creation might have imprinted a direction, a spin, onto the chemistry that would one day become life. This theory is by necessity highly speculative, resting on the knife's edge of quantum chemistry and cosmology, yet its power is in its profound unity. It suggests the story of life's ingredients is woven into the deepest fabric of the cosmos, that the same event that gave us space and time also hummed a specific tune, a frequency that may have guided the first fragile steps from atom to molecule across the silent, expanding dark. A single, perfect origin story is a beautiful fiction. The universe is not a tidy laboratory with one controlled experiment, but a sprawling workshop of infinite chaos and opportunity. This brings us to the final and perhaps most compelling perspective, the convergence theory. It proposes a simple but profound truth. No single pathway we have explored holds the exclusive patent to life's first molecules. Instead, the journey from simplicity to complexity was a grand, multi-stage relay race where the baton of chemical potential was passed from one cosmic environment to the next, each adding its own layer of refinement. The process likely began in the silent, cold nurseries of interstellar clouds. There, on the surfaces of dust grains, quantum tunneling and cosmic rays initiated the first, most basic steps, building simple organic molecules like methanol and glycolaldehyde in the deep freeze. This was the universal feedstock, a raw chemical alphabet written in the dark. Then, as a cloud collapsed to form our solar system, the protoplanetary disk took over. The young sun's ultraviolet light became a new tool, photochemically processing those inherited ices into a richer, more diverse set of compounds within the swirling disk, customizing the inventory for our particular neighborhood. This processed material then coalesced into comets, asteroids, and planetesimals. These were not just delivery trucks but active mobile factories, within their interiors warmed by radioactive aluminum or the periodic heat of a close solar pass. Liquid water pockets formed, allowing dissolved organics to link into longer chains, upgrading the complexity further. Finally, these celestial messengers rained their cargo onto the young Earth and other rocky worlds. Here, the true convergence exploded. Planetary surfaces became the ultimate testing grounds. In deep-sea hydrothermal vents, iron-sulfur minerals templated metabolic cycles. In tidal pools, wet-dry cycles concentrated and polymerized molecules on clay sheets. In the atmosphere, volcanic lightning and ultraviolet light sparked new syntheses. Impact events delivered fresh supplies and created temporary hydrothermal systems in their craters. No single mechanism had to do all the work. A nuclear base formed in an interstellar ice mantle might have been delivered by a comet, concentrated in a tidal pool, and linked into a chain on a mineral surface, all through different complementary processes. The universe, in its abundance, was throwing everything at the wall to see what would stick. It employed every tool in its kit: starlight and stardust, chemistry and geology, fire and ice, patience and violence. The emergence of the first complex molecules was not a singular event, but a symphony of processes, each playing its part across time and space. This convergence is why the search for life's origins is so challenging and so hopeful. It means there is no one secret ingredient or special place. It suggests that wherever the basic conditions exist, a mix of these universal pathways will inevitably begin weaving the tapestry of complexity. The universe is not trying to make life in one specific way. It is simply set up to make chemistry interesting, and from that persistent, multifaceted interest, life, against all odds, found a way to begin. From the fiery forges of young planets to the silent laboratories of interstellar dust, we have charted a universe brimming with chemical potential. We have witnessed molecules assembling in the crushing dark of hydrothermal vents, on the charged surfaces of volcanic ash, and within the fleeting warmth of radioactive asteroids. We have followed them as they hitched rides on comets, were sculpted by the spin of ancient starlight, and may have even been guided by the ghostly hand of quantum coherence. 30 distinct pathways, each a testament to the relentless creativity of the cosmos. This is not a search for a single answer, but a celebration of the many ways the universe whispers to itself, experimenting with the recipe for us. The drive to trace our lineage back to those first complex molecules is more than scientific curiosity. It is a profound human longing to understand our place in the grand story. We are not separate from the cosmos. We are its most intricate echo, built from atoms forged in stars and assembled by processes that seem to hum through the void itself. So we turn the question to you. After this journey through cosmic kitchens and primordial workshops, which theory resonates most deeply? Was it the elegant simplicity of the lipid world where life began with a simple boundary, the dramatic forge of supernova shock waves, or the patient, cold chemistry of interstellar grains? Share your thoughts in the comments below. We would love to hear which cosmic origin story captures your imagination. If unraveling mysteries like this fuels your curiosity, be sure to subscribe and join us for our next deep dive into the universe's greatest puzzles. Wherever and however it began, the legacy of those first molecules is written in every cell of your body, a living inheritance from a time before time, connecting you directly to the dawn of chemistry itself.